In stats today, we started the binomial distribution. So all three of these scenarios here are binomial. And what we did was we looked at what was in common between all three scenarios. We noticed that all three are binary situations, meaning two possible outcomes. So, you toss a coin, you get heads or tails, spin a roulette wheel. While it does have three colors, we're saying whether the ball lands in red or not red. So still two possible outcomes. And for babies, we are saying whether or not they are female or not. So binary. There's a fixed number of trials. We're flipping a coin 5 times, spinning a wheel 8 times, sampling 100 babies. So this isn't an infinite process where we decide ahead of time how many times we're going to do it. That's another property of binomial. Each flip or trial is independent. The results of one trial have no effect on the other trial, which is tied to probability is constant. It doesn't change trial to trial. All right, so those are actually the 4 properties of a binomial distribution, and they're spelled out formally right here. They make a nice little acronym of BINS, if that helps you remember it. But they're, as we just now identified, those 4 things. So moving on. What about these 3 scenarios? Are they binomial? Maybe hit pause, walk through the 4 properties, and check. I'm going to do it right here. I'm going to write down all 4 properties and check each one. All right, option A looks like type O or not, so it is binary. Children are receiving genes from their parents independently. They literally tell us that they are independent. I guess they are for sure having 5 kids. So that's a yes. And probability is independent, so I know probability is 0.25. So that checks out too. It's binomial. On part B, option B, I have a deck of cards, and I'm turning over the first 10 cards one at a time. Notice it doesn't say putting them back. So when I turn over that first card, I have, 4 out of 52 chance of getting an ace. I lay down a bunch of cards. I get to the 10th card. Is my probability of an ace the same? That stands out to me right away, that we're doing this without replacement. Now, there's a rule in sampling where if you have a large population and you sample under 10%, you're safe to assume independence, but this is a pretty small population and we're sampling 10 cards, not independent. Probability changes. This did check out. We had 10 trials, and it is binary, ace or not, but it's still a no, not independent. Last one, still have a deck of cards, still turning over top card, but we're doing with replacement. That's sounding pretty good. So I think we can say success rate is constant, each draw is independent, but it says until. It's not fixed. This could be infinite. We could be here all day until we get an ace. And then I don't even know if I can say it's binary. Like we're going until we get an ace, but yet W doesn't represent an ace or not. So it's a little different. I don't know. I'm not even going to put an X on B because it's kind of binary. I don't know. We'll deal with this later. This is called geometric because of the until. All right, hopefully what binomial is and is not is starting to click. Let's do an actual problem off of option A. So same scenario as option A. We're choosing 5 kids, or having 5 kids, I don't know. And we want to know what are the chances that none of them have type O. So one thing you're supposed to do, we already know this is binomial, but one thing you're supposed to do on an FRQ is identify the distribution, just like on a normal distribution. So we're going to say binomial, N is 5, and P is 0.25. And the question's already typed for us right there. There's a formula at the bottom of this slide, and it looks like this. And you are allowed to use that formula if you want, but there's another option on your calculator that'll do this very quickly. But before we dive into the formula, or actually before we dive into the calculator, let's look at the formula. This right here is number of ways it could happen. Because if I have 5 kids, the X value could cause a success or failure any number of ways. So this one, we're starting easy. If I have 5 kids, there's only one way X equals 0 could play out. And that's all 5 of them in terms of failing to have type O blood. Notice it says success and failure up in the paragraph. So all 5 don't have it. There's only one way this could happen. Whereas if we skip down to X equals 1, I believe there are 5 ways this could happen. Because I could move that S through all 5 spots. And then it gets even harder whenever we talk about X equals 2 or X equals 3 because we're shuffling all these S's around. And it's hard to keep track of. If N increases in size on a problem, it gets way out of hand. So that NX with parentheses, it's called a combination. Your calculator types it like this. The actual way you do it is N factorial X factorial N minus X factorial. So your calculator does all of that when you use this combinations formula function on your calculator. But X equals 0 is very easy. We already know the answer. It's one way. This is probability of success, and this is probability of fail. So for this problem, there's one way, and there are no successes, and there are 5 failures. I hate to say they're failures, but oh well. So we get 2373. So that one's really easy to do by hand. You know, we didn't even need all this craziness down here. We just needed 0.75 to the 5th power because we knew there was only one way this could play out. If we get a more complicated one, like x equals 1, x equals 2, there's a function on your calculator called binomial PDF. And it's going to ask you for trials. We already know that's 5. It's going to ask you for success. We know that's 0.25. And you can actually leave the x blank, and it'll give you the entire distribution of, in this scenario, 5 kids and type O blood. So it'll give you probability of 0, of 1, of 2, of 3, of 4, of 5 kids. It'll give it to you like in a big set notation, I think. But let's get x equals 0 and see if it matches what we just got. So you jump to the calculator. You press menu. You might write this down. So menu, stats, distributions, and you scroll way down the screen. We have 2 binomial options. We want PDF for this problem. We'll use CDF sometimes, but for this problem, since it says x equals, we want PDF. So let's back out. Menu, stats, distributions, binomial PDF. I have 5 trials. I have 0.25 success. See how it says optional there? You don't have to type anything here. It'll give you the whole table. But let's do 0. And sure enough, we get the same exact answer we wrote on the board a second ago. 2373. People get mixed up, and they think that they have to do the formula and binomial PDF. You only have to do one. And AP is A-OK with you doing binomial PDF. So if you're curious, the combinations formula, where is that? Probability and combinations. And you would type 5, 0, one way. Notice it would not be fun if I wanted to do, for example, 3 successes. 5, 3 kids having type O, 10 ways. I'd be sitting there with 5 blanks, shuffling 3 S's around 10 different ways. Chances are I'd miss one. This is very nice. All right, let's do one more and we'll stop. So x equals 1. We could do it the formula way. That'd be 5, choose 1, times 0.25 to the 1st power, times 0.75 to the 4th power. I'm just plugging into that formula you see right above this. Or you can do binomial PDF. And let's see what we get. Menu, stats, distributions, binomial PDF, 5, 0.25, whoops, 0.25 and 1, we get 3955. All right, that's as far as we got on Tuesday. I'll post another video for Wednesday later. See y'all later. Bye.